All right, welcome back. Uh, I've rearranged my office a little bit here at home. You can see Izzy and uh, Lucy hanging out. Izzy does not like Lucy. They don't get along, but you can see they're getting along right now. So I don't know if we hear them yelling at each other, we'll see what happens. I don't know. Anyway, what are we doing here? It's been a few days for me, but I know if you're just watching these videos straight through, um, you're like, Steve, what are you talking about? We're ready to talk about Gibbs equation. All right, let's talk about Gibbs equation, shall we? So Gibbs equation, where we're at, let me stop share. So we go here and let's look at that. Now, so we need to derive Gibbs equation. Now, again, I think I've mentioned this right at the very end of the last video. For me as an engineering faculty member, I don't expect you to um, do a derivation from scratch. You're engineers, you're not mathematicians, you're not scientists. Now, that's my personal opinion. That's my approach. It's up to your instructor how they want to be about that. But I don't really push being able to do derivations. However, you do have to know how a derivation works. We have enough math that we could do that. Where does Gibbs equations come from? Well, it actually, a lot of derivations will start with the first law, right? And we're going to use a kind of a simplified version of the first law using a traditional sign convention, this idea of Q net in minus W net out is equal to delta big U, basically, right? And and we don't have to keep the net in. We can just say Q minus W equals delta U. And we just understand that's using this traditional sign convention where heat in is positive and work out is negative. Again, we've talked multiple times. That's not the way your textbook approaches the sign convention. But it's okay. It works. It's just fine. Let me see if I can straighten that camera just a bit. There we go. I don't know. Maybe that's a little better. We'll roll with it. Again, that's a traditional sign convention. You don't have to use it. We're just going to use it for this derivation. Q minus W equals delta U, where work out is positive, where heat in is positive. Okay. Now, if we consider a differential slice of our system. Well, we talked before about heat and work being maybe dependent on more than one variable. All right. So we have to use inexact differentials for these because they may be dependent on more than one variable. They might only be dependent on one variable. They're probably dependent on more than one variable. The U value, on the other hand, that is dependent only on the state of the system. So that's one variable. So we'll use a regular ordinary differential for that. All the same, what are we talking about? These are tiny little slices of our system, differentially, infinitesimally small slices of our system. Now, okay, well, recall we recently talked about that for a reversible situation, a differential slice of heat transfer is equal to temperature times a differential entropy change. And also because work is equal to the integral of pressure with respect to volume, if I take the derivative of both sides of this equation, I have a differential slice of work is equal to the derivative of an integral is just the argument, P dV. That might not be the best way to say that, but hopefully you guys get the idea, right? If I take derivative of both sides of this equation, this is what we're left with. So if I plug this in for dq and I plug this in for dw, this is what we're left with. We get T ds minus P dV is equal to du. And then if we divide by mass, well, the temperature and the pressure are not what we call intensive properties. They don't depend on the mass. These are environmental conditions. However, these three state variables, entropy, volume, and internal energy, they do depend on the mass. So if I divide everything by mass, I get the lowercase version of those variables, the per unit mass basis of all of those. Okay. Now, Steve, what the heck are we trying to do? You're showing us this crazy differential equation and what are we trying to do? What are we trying to do? Remember, our goal here, what we're trying to do is we are trying to determine a change in entropy. And we said that Gibbs equation is one of three ways we can determine that change in entropy. So what I need is I need to solve for this ds here. And that's what we're going to do. I'm going to solve for ds. So if I solve for ds, well, I'm going to move PdV to the other side of the equation, then divide everything by temperature. So this becomes P over T dV plus du over T. And normally we would write these, I would write the du over T first and the PdV first, which I'm just going to do that. A bit overkill, but this is normally how we would present it. Right? Now, one might say, well, Steve, what the heck, man? I'm still trying to get this to not be crooked. Apologize. I thought I had that worked out. I think I've got the camera at an angle. I think that's why. All right. Steve, okay, well, that's a differential. That's a differential change in entropy. This is a differential equation, unless you had a lot of extensive work with differential equations, one might look at this and say, Steve, how does that help us? I don't know what to do with a differential equation. I know I'm not expecting you to, in a Thermodynamics 1 course, know what to do with a differential equation. Just like we do with the first law and the second law, let's get this down to something that's more usable. But this is, in a raw form, this is Gibbs' free energy equation. Allows us to describe a change in entropy. Now, before we turn this into something useful, let's do one more thing here. There's another kind of alternative version of this, right? Another thing to recall is, by definition, enthalpy is the sum of internal energy plus pressure times volume. Now, we would never actually mathematically solve these out or compute H this way, but you can, because H is often already done for us in tables or other methods, but this is a way you can get to it. Now, what we need to know, though, is what I want to show you here is, notice that these are all differentials. Okay, well, let's look at a differential form of enthalpy. So if I take the derivative of the left-hand side of this equation, that's equal to the derivative of the right-hand side of the equation. Well, derivative of h is just dh, derivative of u is just du, but here I've got to do a product rule. Now I've got two variables there, I got to do a product rule. So this becomes p dv plus v dp. Or, if you like, dh minus v dp is equal to du plus p dv. And notice in this last line on this, which I've been very careful here to keep this last line, because notice that du plus p dv here is equal to dh minus v dp. Both of these are divided by the same temperature, so the same denominator, so I can basically put those together and substitute this in for that, and then write the change in entropy which we've already solved one way to be du over t plus p dv over t. That's still true, but I'm going to substitute in here and say this could also be dh over t minus v dp over t. And then what I've got is we have to figure out, okay, is there a situation where I know how U relates to temperature and how pressure, volume, and temperature relate to each other? Can I think of a situation or a substance or some rule that allows me to relate U to temperature, pressure, volume, and temperature to each other, or H to temperature, and again, pressure, volume, and temperature to each other? Right. And here in class, I'll ask that a couple of times and try to ask it a couple of ways and get us to think about it. Because I'm wanting an answer. I'm hoping, and I'm kind of stalling a little bit, hoping you come up with an answer. Do you know of a substance or a law or a rule or a situation where I can relate U to temperature and pressure, volume, and temperature to each other? What comes to mind? And the hope is that somebody helps me out, says, what about ideal gases? Yes. For ideal gases, we do know how we do know that du is equal to C sub V dt, and that dH for an ideal gas is C sub P dt. And I also know that P little v is equal to RT, which I can solve that in two different ways. Here I need P over T. So I can say, well, P over T is equal to R over V. Or if I need V over T, I can also say that V over T is equal to R over P. So I've got this differential equation that I can't really do anything with unless I've got a lot of tools with it, but it's actually pretty simple. Let me show you. Well, it's actually really not that simple, but let me show you what we can do to get this to something that's useful for us. Because right now in this differential form, maybe it's not so useful. What we know is for ideal gases, I can plug these things in. So let's start with one form. Let's start with just maybe just yeah, we'll just start with the left-hand form first, right? So let's plug in. I'm going to say ds instead of du. I'm going to plug in c sub v dt. So is equal to c sub v dt over t. And then I'm going to plug in for p over t. I'm going to plug in r over v for p over t. So this is plus r over v dv. Right? So let's work with this left-hand side first, and we'll worry about this right-hand later. Let's worry about this left-hand side first. Okay. Now, what we often do in this class for differential equations like this is we say, well, let's integrate for a process from state 1 to 2, because how often do we deal with something that goes from a process from state 1 to state 2? A lot. A lot of times. It's kind of our most common bread and butter thing that we do. So for a process from state 1 to 2, I'm going to integrate ds. Well, and all I'm going to do, I'll go ahead and write it out. All I'm going to do is I'm going to integrate both sides of this equation from states 1 to 2. This is going to get integrated with respect to temperature. This one's going to get integrated with respect to volume. And this is just the integral of ds from 1 to 2. Well, that just becomes delta s. So this is, now again, these are little s's. Remember, all the way back here, remember we said divide by mass all the way back here. So these are little s's. These are specific entropies. Little s's. I know my little s's look a lot like my big s's, and my big s's look a lot like integral signs. I warned you guys. Sorry. Delta s. And then we're gonna, you know what? Let's leave the second guy alone for the moment. We'll talk about him in just a minute. So this is now, again, I'm integrating with respect to temperature. So it's going to be from T1 to T2, C sub V dt over T. Okay. Now this one's getting integrated with respect to volume. Okay. Now let's look at this guy. Let's think about this. I'm not integrating. Well, that's a nice stopping place, and we'll pick up the next video from here.